All right, good afternoon, everyone. As you enjoy your lunch, my great pleasure today to introduce Professor Thoma. As you can see from the slide, he is the Director of Agricultural Modeling and Lifecycle Assessment in the Colorado State University. And I would say Dr. Thoma is really one of the world leaders in the field of systems modeling, lifecycle analysis of food systems, with a very nice dairy cow, as you can see from a photo here. And he has a lot of collaborations with Cornell researchers, like Professor Christine Rhee, who is going to join us soon. And before, starting at Colorado State a couple of years ago, right? I mean, he was a professor in the University of Arkansas, and I just learned that he has been in Arkansas for almost half a century. A long time, residence there. Anyway, so please join me to welcome Professor Thoma to Cornell University, and let's look forward to his presentation.
Thanks, Coach. Today I'm going to give you a quick introduction to lifecycle assessment. How many of you have heard lifecycle assessment and can do more than spell it? All right, one of you can do more than spell it. That's good. So I'll give a high-level introduction to LCA, the framework. Then I'll run through sort of a smorgasbord of examples from probably the last 10 or 12 years of work that I've done in LCA. And then I'll sort of close up with some special considerations of LCA and food systems. And since you all are mostly eating lunch, you'll appreciate that we're talking about food and nutrition by the time we get to the end of it. So let's see if I can run this clicker. No, I can't. Line remove it from here. Or not. One of these buttons will work. That's the laser.
Oops. Well,
A minute ago.
What about a keyboard?
Yeah, just push the keyboard. Oh, there we go. Okay.
That's
So just a quick introduction to AgNext, which is the entity within Colorado State that I work for. We are focused on livestock systems as a part of a nutritious and sustainable food supply. Our mission is to identify scalable interventions in livestock systems that will improve sustainability and support the industry, make them continue to be profitable, and support local communities. So that's kind of the mission and vision of AgNext. Let's see. Let this go. So I'm sure all of you are quite familiar with the broad concepts of sustainability. It's this sort of triple bottom line: economic, social, and environmental. And the little sweet spot in the center, of course, is very difficult to achieve. Society is increasing in its desire to understand the sustainability characteristics of our food systems, and currently climate change is a dominant factor in the thinking around sustainability, but it's really multidimensional, right? There's water issues, which are going to become as or more important than climate issues in the next several years, I'm certain. There's also a colleague of mine in the School of Business at Arkansas said, if it's not economically viable, it's not sustainable, right? So if it's not going to be the economics here, if you can't make a living at it, it doesn't matter how friendly you are to the environment, you're not going to stay in business. In food systems, one of the things that's really critical is thinking about nutrition security. And so we think about supply chains and distribution and how can we manage or avoid food deserts, right? We know that there are lots of people in dense urban areas who have difficulty finding high quality nutritious foods. And so thinking about the food system as a system, right, is an important component. I won't focus so much on the downstream stuff for most of the rest of my talk, but wanted to highlight the nutrition piece because we'll come back to that for sure. So recently realized that I have high blood pressure. And so, right?
Just recently.
Well, fairly recently.
And you're healthy.
And before I knew I had high blood pressure, right? I didn't do anything about it. I ate all the salt I wanted, whatever I wanted. Now that I'm able to measure it, I can manage it. Same with your checkbook, right? If you just spend and spend and spend, and you don't ever measure what's in your checkbook, thankfully it's a lot easier than it used to be before we had the, the paper ledgers back in the day. But if you don't measure it, you can't manage it, right? So, how do you measure sustainability? That's the question that we'll try to address a little bit today. So, what sustainability means, right? The American Indians have a saying about the seventh generation. I don't know if you've seen the seventh generation consumer packaged goods brand, but the idea of thinking about what we do today will impact 7 generations in the future. So resource conservation, resource use efficiency is really important. One of the things that's fascinating to me, in New Mexico, there are copper mines. Well, there were copper mines in the 1800s. And the ore in the remaining mines has less copper in it than the waste piles from the 1800s. So now they're processing the waste piles because there's more copper there than digging down into the ground. So we are depleting our resources. Copper, of course, is important, but not as important as food, it turns out. So having measures and metrics allows us to do the things that are bulleted here. We can document and track progress so that we know we're moving in a more sustainable direction. It also gives, because society is really interested in this topic, right, and food is really important, it supports the social license to operate, right? There's a lot of animal welfare advocates who want to stop animal agriculture altogether, right? So until we can demonstrate that we're doing things in a good manner, those kinds of attacks on agriculture will continue. And so it supports the social license to operate. And last thing on the slide, lifecycle assessment is a framework for measuring and quantifying the measures and metrics of sustainability. So, a quick introduction to LCA. It is an iterative process. It's governed by a series of international standards, the 14040 and 44, the foundational ones. Starts with defining the goal and scope. Fundamentally, it's an accounting framework, and so it's also fundamentally a modeling framework, and you build models to answer questions, and you have to build them to answer specific questions. So why do you do the study, right? That's a critical starting point for an LCA. And then you collect inventory. We'll spend some time on that. This is so if any of you are engineers or chemical engineers in particular, you know about mass and energy balances, right? So keeping track of the flows of material and energy through a system is what the inventory is. Impact, what's the carbon footprint? What's the water footprint? What's the eutrophication impact, right? What are the human health impacts of the activities in the supply chain that produce the good or service that we're interested in? And then interpretation, what do we do about it? So some of the things that we can do are over on the other side, right? So product development, so very early in the product development process, right? Where we're thinking about the ideas. If you do an LCA, you don't have very much data, but you can design things that will be better for sustainability by thinking about, if I'm gonna design a new laptop, should I build it in a manner that makes it easy to disassemble? Right, so that we can reuse those parts at its end of life. It's easy to implement design for the environment in the early stages, even though the data quality is low and the data may not be entirely available. We can also use it for benchmarking, right? So people are interested in, Walmart, for example, has the gigaton challenge, right? They're going to try to remove a gigaton of carbon from their supply chain. Well, how are they going to know how to do that if they don't know where they are today, right? What's the benchmark? What's the standard against which we're trying to build those reductions into the supply chain? So benchmarking, we can use it for labeling. We have to be careful about labeling. How many of you know the company Tesco? It's a large consumer packaged goods company in the UK. 10 or 12 years ago, they spent a lot of money with the consultants to get carbon footprints for like 1,000 of their products, and one of them was potato chips. So they had potato chip A and potato chip B, and one of them was 10 grams of CO2, and the other one was 5. Guess which one sold? 10, because 10 is better than 5. That really happened, right? So just managing it doesn't help if we don't have this interpretation. What does it mean, right? How do we use that information to make smart decisions? So you might be wondering why there's a little baby on the chart there, right? It's, that baby in a diaper. This is my favorite example of how to think about a functional unit, right? So the thing about LCA is it's often used for comparing two products. But you can't compare a Coke and milk. Well, you could, but it would be kind of silly, right? You can't compare an elephant and a laptop. So the function of the thing, the two systems, has to be the same. So my question to you, this is going to be a short period of interaction. What is the functional unit for comparing Pampers, to borrow a trade name, and cloth diapers? Right? What's the proper functional unit? What's the function of a diaper?
Your day of hygiene.
1 day of hygiene. It's a good start. Sometimes I say it's to keep my couch clean. But that's not, so yes, that's a good start, but it's incomplete. Is it one pamper or 1 day? Is it, right, how many cloth diapers do we use in 1 day versus how many Pampers? Is that, how do we define the reference flow, right, for 1 day of cleanliness? Any other thoughts? Good start, expanding upon that idea.
Amount of baby excreta.
The amount of baby excreta. Directionally correct as well. Over what time period, for example, might we ask? A day, a month, a year? As it turns out, fascinatingly, if you put your child in Pampers, right, the water absorbency of that material is really fantastic. They will pee in their Pampers before they'll go to the toilet, because why not? So it turns out that it takes 3 years to potty train a child in Pampers and 2.5 years in cloth diapers. So the proper functional unit turns out to be 1 potty trained child. And 3 years worth of Pampers, 2.5 years worth of cloth diapers with all of the, soap and hot water and everything that it requires, and anyway, you get the picture. Thinking about the function of the system matters, right? So measuring it matters, what you measure matters, and we'll find out that how you measure it matters as well. So there's a little bit of repetition in this slide, right? So we have the multi-step procedure that we saw in the cartoon in the previous one. We just talked about the functional unit. We talked about the system boundaries. This is a cartoon of a multi-animal, so multi-animal with pigs and other animals on a farm. We've got inputs coming in. We've got all of the things that happen in each of those unit processes within the system. And over here, we produce pork meat that's consumed, right? So that's our main product. And so we define our function as providing a certain amount of pork to the consumer or some other set of characteristics that we can add. But down here across the bottom, and it may be a little bit difficult to read, there's a bunch of other things that the system produces. And so the system as a whole, as well as perhaps any of the individual activities within that system, can be multifunctional. They have more than one product that's produced by that system. And so in LCA, which is an accounting framework, we have to be able to say, okay, we've got all of this carbon dioxide that's emitted from this whole system. How much of it goes here? How much do we assign here? How much do we assign here or there or the other way? Which of those products gets how much of that footprint? So it's well, I started with the dairy sector in 2008, discussing allocation, which is this, we'll come to the more clear definition of allocation, and we finally resolved it in 2022, mostly. So it's a thorny problem in life cycle assessment, this question of multifunctionality. And there are two paradigms, attributional and consequential, that are commonly adopted for handling this question of multifunctionality. So attributional systems take the pie and slice it, right? So the pork meat gets this big share, and the bone meal and the blood meal gets this share, right? We just take it and we divide it. It's a very satisfying paradigm from an engineering perspective, right? Because we look at the system, we see all those things coming in, we put an umbrella over it, and we calculate all of the emissions, and we just divide it up and say, you get this much, you get that much, right? Straightforward, except that it's not, because there's no scientific basis for making a decision about whether we should use revenue or protein content or energy content or, right, whether it's aligned with the stars, who knows, right, what the right way to do it is. The other approach is called the consequential model, and what it does is it says, let's look at the effect that our system has in the broader economy. And I'll give a better example of that in just a minute. One quick thing for those of you that are math nerds, life cycle assessment is when you collapse it all down and you build it out and you try to do the math at the end, it's inverting a matrix. And matrices have to be square to invert them, right? Everybody remembers that from linear algebra? So here, if I've got a matrix and across the columns are labeled with the things that are being consumed, and the rows have the things that are being produced. Maybe I have that reversed, doesn't matter. And if I have a multifunctional activity, right? So let's say a dairy, and it produces meat by the cold cows and milk. If I'm in this model and I want to know what's the footprint of the milk, the mathematics of it is I split the column that says dairy into a column of milk and a column of meat. Likewise, over on the rows, I split that into a row of milk and a row of meat. And then each of the places where there's an input, I divide it, right? The consequential paradigm says, well, here's milk. Down here is beef. There's no input of beef to the dairy system, so I'm just going to put a negative number there. My matrix stays square in both cases. So mathematically, you can mix and match these two things. Please don't ever do that, because it gerrymanders your system and makes the results really difficult to interpret. So keep them separate. Mathematically, you can, but don't. Okay, so an example from dairy. Should we intensify dairy production? So there's a very effective tool in the dairy sector called Remensin that increases the animal's milk production and doesn't cause them to increase the inputs, right? It just makes them more efficient at producing milk. So the question is that a good thing to do from a sustainability perspective? And if we take an attributional model, typically we'll see about an 80-20 split between the milk and the meat, depending upon whether you use protein or energy content or revenue. It shifts around a little bit. But if we intensify our production, right, we hold the inputs constant, and we increase milk production, the answer will always be intensification of dairy production is beneficial. Can't get another answer. With the consequential paradigm, as I said, right, we basically put a negative sign in our matrix, which provides a credit, right? It subtracts emissions from the dairy. and the quantity of emissions subtracted is equal to the amount of beef that the dairy produces. So if we intensify, the thing that happens that we have to think about here is that in the marketplace, the demand for milk and meat don't change because we added rumensin to the dairy. We still have to produce the same amount of meat that we had before, but now we have less meat coming from, we have some meat, right? So we still get a little bit of a credit, but we don't have as big of a credit here because we have to produce that other beef somewhere because the market still demands it. So thinking about it from the market paradigm rather than the engineering paradigm, it is possible that the amount of beef that needs to be produced here has enough of an impact. We add back enough burden because we're not displacing as much beef that we could, in principle, reach the conclusion that intensification is not a good idea. Right? So it's a really important thing to understand that you don't often, but you can get different answers. And so when you read the literature and you see somebody has done a consequential model versus an attributional model, that matters, or at least it can matter. It doesn't always. Okay, so we're gonna skip past those, and we'll talk about activities. The core of LCA is a unit process. And when I first was introduced to LCA in 2008, a colleague said, it's the thing that you collect data for. That's pretty unsatisfying for an engineer, right? So the thing you collect data for could be a pump or a refinery. It could be a cow, or it could be the ruminant sector, right? Whatever you have data for. It could be, so if it's a manufacturing facility, you might have sub-metered data for the water that's being used in each of the processes. Or you might have water just for the whole facility, right? So you have to take that with, you have to build the model with the data that you can find. This is just a cartoon of the beef system, right, with raw materials coming in, and right, each of those photos there has to have activity information, material and energy flow through each of those things has to be calculated. So for the cow calf, right, how much grass did they eat? Because the quality of the grass affects the quantity of enteric methane. How much enteric methane do you expect that they emit? And all the way through, right, for the cleaning chemicals at the harvesting facility, et cetera. So all of those things have to be tallied up. In agriculture, which is of course the foundation of food systems, we can't measure all of this stuff. Right? Nitrous oxide is a tremendously potent greenhouse gas. It comes from the biogeochemical cycling in the soil that's related to the animal-plant soil interactions. There's fairly easy stuff like how many hours did we run the tractor and how much fuel did it use. That's pretty easy to get. But some of these other things are harder. And so what happens often is that we use process models. So some of you may know of the Rufus model that's being led by Kristen, and thank you, Chris, and I have been working on. It's a model that is trying to connect all of these things in the context of the dairy. And so we don't often have data, so we have to do systems level modeling as well. Okay, so following along, we talked about the golden scope, functional unit, system boundaries. We talked then just a minute ago about the inventory, right? Collecting all of the data around the system. So the inventory will look like this, except that it goes down about 15,000 rows. And so who can make a decision on 15,000 items? Nobody, right? It's impossible. So what the LCA community has done over the last really 3 decades. By the way, does anybody know when the first LCA was performed? 1976. No, a little bit earlier than that. You know who did it? Coca-Cola did, yeah. They were asking plastic or glass bottles was the question in the mid-60s, I think. Maybe it was 76, but it was longer than I thought. And we know which one
What
they
metric
chose.
were they using?
Yeah,
Just
well,
cost?
Probably it was driven by weight, right? Weight difference. So we have a list of these categories, right, that I mentioned some of before, that are called midpoint categories. They can be combined into these so-called endpoint categories. The things at the end of the day that we really care about are human health, not carbon footprint, right? I could care less about carbon footprint, but if carbon emissions have an adverse impact on ecosystems or humans, that's what I really care about. This is a nice directional indicator. Not that it doesn't have utility, but it's not the fundamental thing that we care about. And so I was just working with a colleague who's writing a paper, and he had some confusion about single scores. And so I thought it would be good to show this slide, because you'll come across sometimes what they call single scores. And so there are causal pathways, right? So global warming, greenhouse gas is emitted, it causes radiative forcing, causes the temperature to go up, and we get a carbon footprint. We can normalize and weight all of those things and get a single score that's often reported as points, which has always been a weird thing for me, but it's a measure of the accumulated impact of all of these things after they've been normalized. So what do we normalize global warming against? Well, it could be all of the GHG emissions from the United States, or all of the global GHG emissions, right? So figure out what the total emissions of each of those are, figure out what fraction of those emissions your product system is providing. That's the normalization step. And then we say, well, societally, greenhouse gases are really important, so we'll give it a weight of 1, and we'll give these others a weight of 0.5, or whatever it is, and you can come up with a single score. There's another entire approach that's based on what we call endpoint damages, in which, so here there's no causal connection between the midpoint category and the single score. Over here, we look at, let's say, global warming, and we try to articulate the mechanisms by which global warming causes an increase in disease, right? So in sub-Saharan Africa, global warming is going to lead to more flooding, it's going to lead to more dysentery and typhoid, right? So those are causal connections. So there's a different underlying paradigm for these two things. So this is the so-called endpoint categories versus midpoint categories that are normalized and scored. So those two things also, when you're reading the literature, are important to consider. And I'm going to run out of time here, I can tell. On the left-hand side of this, right, if we're talking about global warming, which was a bunch of greenhouse gases, those are relatively easy to measure, but it's easier to support decisions if we move to the right? So if we have just a single score, right, 2 is worse than 1, so that's easy decision to make, right? If we've got 18 of them, how do you balance it? The problem with the single score is that you might have some trade-offs that you lose. Similarly here, you can have that same problem when you end up with a single score. Okay. High-level challenges of food systems, hard to get data, often modeled. It's spatially and temporally variable. They're dynamic. LCA is typically static, so you have to think about coupling process models with LCA. Almost exclusively, we model impact, not potential benefits. It's incomplete. Carbon sequestration and nutrition are 2 that we'll touch on in just a minute. Carbon sequestration, everybody has heard about, right, indigo ag, right, and trying to pump carbon into the soil? No? Has everybody heard, or anybody heard about carbon sequestration as a thing that is important for agriculture? Good. So the question here is, if I put 1 atom of carbon into the soil, does it offset burning 1 atom of carbon in a diesel engine? And the answer is it depends. And it depends on what? It depends on if you're doing a stoichiometric balance, then yeah, 1 for 1, no problem. But if you're talking about carbon footprint, no, because the carbon footprint of that diesel has as an underlying assumption, it will continue to warm the atmosphere for a century. So if I don't keep that carbon in the soil for a century, they are not equivalent. Unfortunately, all of the carbon markets are based on this, which means that as soon as you put that carbon into the soil, and we know that it goes up and down every year, right? Every time it goes up, you burned more diesel. Every time it goes down, you save diesel. And so the consequence of that is it will be very expensive to measure and monitor and verify that your soil carbon is really beneficial to the climate. So, all right. So I'm going to give you a smorgasbord now of results from various studies. One of the things we can learn from LCA, some things matter more than others, right? You can see the 2 blue circles there are places where we would think those are probably good places to target interventions to make the product better. This is from the study that we did when I was at the University of Arkansas, where we looked at the carbon footprint of milk. This is the farm gate, so it doesn't include the pasteurization and distribution, etc. And there, across the y-axis, there's the fuel, so on-farm fuel consumption, enteric methane, the production of feed and manure, and then the combination over here on the far right. What's fascinating about this slide is that there is a really wide variability. So we surveyed 539 farms, and we did an LCA on all 539 of them. And this is the box and whisker chart result. So the boxes are 25 and 75, the gray bars are 90 and 10, and the individual dots are the rest of the results that we got. So what this tells us is there's a huge variability in the current system. And if we could figure out what these guys are doing differently than these guys, we might be able to bring the whole sector better, right? So we should focus on making these guys better more than we should focus on making these guys better. It's really hard to do that, right? But that's what we should do. So if we were to do that, this is the scaled up full supply chain for milk. It's about, and this is somewhat dated. At the time, it was an average of 35 teragrams across the entire supply chain. We asked the question, what if we took the manure management practices of the bottom quartile, the best performing quartile, and we used that profile of manure management system across the entire sector? We would see that change. It's pretty significant, right? And that does not require new technology. That's just improving the bad actors. I don't hate to call them bad actors, but improving the poor performers, right?
Yeah. But can I ask a question?
Yeah, sure.
So how would you account for the meal quality here? Because every cow is different, and I would assume the meal every day is also different. There's different, I don't know, I mean, we have experts here, but I assume the protein level, I mean, there's so many indicators in terms of meal quality. Even like go to the grocery, they have different prices.
Right, so in this study, it was sort of a national scale study, we quote, corrected for milk quality by using fat and protein corrected milk, right? So we normalized everything to 3.3% protein and 4% fat. So a Jersey animal that produces 5% fat, right, we theoretically diluted that milk, right? So it brought that fat content down to 4%. So but it doesn't capture the grass-fed versus organic, right? You don't capture all that nuance.
There's some kind of normalization, especially with how much water involved, right?
Exactly, yeah.
Because there's story people put that water into the meal.
No, nobody does that.
People in some countries, I know that.
So turning to a beef study, across the x-axis, well, the 3 panels are climate change, land use, and water consumption. And then the different colored bars are the different activities within the production system. And then we've got different regions. And so we've got on the far left there in the northern plains, South Dakota, eastern cow-calf, Nebraska, western cow-calf, and then in the south central we've got Oklahoma. They're all cow-calf operations. Everybody know what a cow-calf operation is? Does anybody know what a cow-calf operation is? So the beef supply chain is cows and calves, right? Cows get pregnant, they give birth, they suckle the calf for about 8 months until they reach 700 to 800 pounds. Then they go into another stage called backgrounders or stockers, and then they go to a feed yard, typically where they're fed corn grain until they're old enough to slaughter. So this is just focusing on the pasture part of that animal's life cycle. And the point I want to draw here is that you can see that location matters, right? So over here, this orange bar is the field emissions, which is dominated by nitrous oxide, and it has everything to do with soil type. So those are probably high clay soils, which tend to become anaerobic more easily, and the biogeochemical cycling and the carbon nitrogen cycle leads to more nitrous oxide being emitted. And so what can those guys do? Yeah, boy, that's tough, right? What is an intervention that would fix that kind of an emission? It's not simple. Turning to a higher scale. So we did a study where we compared diets, right? Whole diets in the US, and the different panels are acidification, carcinogens, which one here's climate change. The black bar is the current estimated US diet, which has, maybe hard to read, CCP, current consumption pattern, 2547 calories per day. And you can see, then we've got recommended 2,000 calorie, recommended 2,600 calorie, recommended 2,000 calorie vegetarian, and recommended 2,600 calorie vegetarian. So we're comparing what we eat today with what the healthy food, My Plate, whatever it's called, recommends that we would eat at either 2,000 or 2,600, and then the two vegetarian. And you can see interestingly for the climate change, right, the current consumption pattern is lower carbon footprint than the recommended consumption pattern, and not significantly different really from the vegetarian. Interestingly, over on carcinogenics, look what happens. They all go up when you start eating basically less animal protein. The recommended is interesting because there's about 3 times more milk that's recommended in the RCP. Long story short, diet matters, but it's complicated. Figuring out what is a sustainable diet when we look at these trade-offs is not necessarily a simple thing to do. And some of the differences we saw on the previous slide are driven by food loss. We know that food loss is critical. We also know that there are differential food losses. We don't waste as much meat as a fraction of consumption as we do fruits and vegetables and dairy. Right? So when you shift the pattern to more fruits and vegetables and you don't modify behavior to change the consumer behavior of food waste, you can end up with consequences that you didn't intend. So food waste matters. This is just a quick slide on strawberries. And look for food waste. It's in the top 3 in all of these categories: global warming, eutrophication potential, water, fossil resources. So a 10% change in food waste, it wags the tail, right? Yield is, of course, the dominant factor in terms of sustainability, which goes back to that intensification discussion with milk and meat. But food waste is an important thing to consider. I'm going to skip this slide and go to this one real quickly. Sometimes you get unexpected results. The result that I didn't expect here was that I am not driving it. Somebody else, because I'm not touching it. Who's driving the mouse?
Oh my. Oh. Somebody's taking over?
All right.
There you go.
Oh. Got a gremlin in the machine.
Oh, is that, you know, the eyeball tracking control? They are looking at Oh, really?
I wasn't ready for
I
it.
hope it's not being
Okay, short version, right? If we cook it in an open top vessel versus a pressure cooker, it makes a huge difference in the entire footprint, right? Including all the way back to the production of the pulses, right? Chickpeas, lentils, dry beans. So it's a really, at least for the chickpeas and dry beans, it makes a huge difference, not as much for the other two. So there are interesting things that you can find out. Okay, so I'll go quickly through this nutrition and LCA so that we have time for a little bit of a question. So, right, nutrient delivery and nutrient security is clearly an important piece of the sustainability of food systems. So the question that LCA practitioners have asked is, how do we include or account for nutrition and nutrition quality in an LCA? And the problem that Adam Gronowski in this paper demonstrated is that it matters what you take as your denominator. Do you do it on the left-hand side per 100 grams of product, in which case meat and animal sourced foods have a very high footprint, or do you do it on a kilocalorie basis, in which case fruits and vegetables have the highest footprint? If we did it on kilocalories, the answer would be eat sugar, because it has the lowest carbon footprint per kilocalorie of anything. So just eat sugar if you want to have a low carbon footprint diet, and you'll be fine. I promise. Yeah, you'll be fine. So it's a challenge, right? How do we do that? So I thought about this a little bit, as have others. And so, is it a function or is it an impact? Right? Do we consider nutrition as a function of the food that it delivers to us, or do we consider the impact that food has on our health? Right? We could do either. So it sure makes sense, right? Yeah, it clearly delivers. It clearly delivers. The problem is that sometimes, well, what do you choose? Do you choose kilocalories? Do you choose protein? Do you choose, right, something else? Right? You're going to get a different answer every time you do. We don't really need different answers, right, to make decisions. So it's problematic. Likewise, nutrition is well known, and so thinking of it as an impact also makes sense. And this is the one that I strongly support. There's a middle ground. There are things like the NRF 9.3 and 15.3, which are nutrient-rich foods index. So the 9 means there's 9 nutrients, and the 0.3 means that 3 of them carry negative scores. So salt, added sugar, and saturated fat reduce the NRF score. You could use that as a midpoint, just like we did for carbon footprint, right? It's an indicator directionally. Whereas the endpoint will say if you eat more fruits and vegetables, you're going to live 3 years longer, or whatever it is, right? We know this from large-scale epidemiological studies. And so this thing called the cone LCA that we talk about just for a second says, let's look at the endpoint, right? You remember the slide that I had with midpoint and endpoint, the single scores, the one on your right-hand side, right? Where we collapsed all of those things into a human health score. That's what this one is, right? The human health impact, and it's reported in disability-adjusted life years, which is the same thing that the epidemiologists report for food health-related risks. And so if we see what's in our diet, and we see what it took to produce it, we can get a human health impact. We can also get the human health impact associated with changing the diet or with a diet. And those things both have units of Dalle's, and so we can add them together. It's a very nice way to think about food. And we did that in this study. So the system diagram for the yogurt, strawberry yogurt production and consumption, and we had several, 5 different permutations of strawberry yogurt, and you can see that the carbon footprint is not dramatically different for these 5 products. So the climate change was here, but if we look at the benefits of increasing dairy and fruit production, look at the numbers there, 65 and 15 versus everything less than 10. The combination of nutrition and environmental impact is possible, and it gives us interesting results, right? The potential benefits of dietary change can offset the potential damage that comes from the production system, right? So again, what you measure matters, right? If you don't include nutrients and health in your analysis, you'll come up with a different conclusion than if you do. So all that stuff matters. Okay, so we need to ensure that future generations can provide for themselves the way we have. We need a systems framework to monitor and manage and measure our resource use efficiency, the environmental sustainability pieces of it. What and how you manage matter, and LCA is maybe the only tool that we have at this sort of a scale that can help us answer those questions. And with that, we have all the time you guys have for questions. So,
Thank you. Very nice introduction and discussion. So, open for questions. Go back.
In your opinion, just because of like carbon footprint and accounting of different footprints across different categories, my question is really just, do you believe that we should account, like when you look at those footprints, do we count all of those towards one stakeholder? So primarily, do we put the burden of like addressing those footprints on the producer, or do we put it on the consumer? What's your thoughts or opinions on kind of who takes the responsibility for each of these components?
so I should have skipped this slide, turns out. So it's a really good question, right? Who is responsible for it? And so this slide shows what happens when food waste occurs in the fluid milk supply chain. So the blue bar on each of the supply chain stages is the emissions associated with that location in the supply chain. The green bar is the induced emissions that physically occurred here on the farm because of loss of milk in the processing, loss of milk in distribution retail, and food waste at the home, right? So this didn't happen at the home. It happened on the farm, but it happened because little Johnny didn't eat his milk and mom threw it down the drain, right? Right, you put your bowl of Cheerios, right? Cheerios are all gone, there's all that milk left. What do you do with it, right? You dump it down the drain, probably. So that's what this is. And then this is the induced loss at retail because of waste here. And so the assigning of that responsibility, currently, all of this is assigned to somebody up the supply chain. And so with this kind of an accounting, we can begin to have that conversation. Then there's the whole GHG protocol of scope 1, 2, and 3, which I don't like very much, but it's out there. So, yeah. You had a question.
You said for the life cycle assessment, there are some data that we can easily get. For example, the amount of time we operate the truck. And there are some other processes that we don't know get easily data for. And we use models. Could you give us some example of what models?
Oh, yeah, sure. So the models that I use mostly are biogeochemical models, right? Because or the CNCPS model that's developed here in Cornell for enteric methane. The Texas A&M Blacklands has a model called Apex, which has about 100 crops that you can simulate, and you can put in. I did this field activity. I planted this crop on this date, and I have this weather file. DNDC it's called DNDC, denitrification, something. Decomposition, I guess. Sure, I don't know. But DNDC, which is managed by an organization called Regrow right now. There's a model that a colleague of mine uses called EcoSys, which is it's a biogeochemical model of soil. There's also the Descent model from Colorado State, and there's a new version of that, or not a new version, an enhancement of it called MEMS, and I'm not sure what MEMS stands for, but it's a more detailed model of carbon pools in the soil profile. There's a model from a colleague named Al Rotz called the Integrated Farm System Model, which incorporates the Descent model for the soil, and he uses some of the CNCPS model for the cow's rumen, and it's a whole farm model, and then the model that we're working on now, which is the Rufus model. And I'm sure there are others.
SWOT, water quality impacting use SWOT.
Sure, SWOT, yeah. Yeah, there's a bunch of them, and unfortunately, they don't all get the same answer.
All the models are wrong.
Yeah, it's kind of like the climate scientists, right? They've discovered that the ensemble modeling gives a better average result than any one of the models itself. So.
Which LCA approach is more appropriate in this case out of like the attributional or consequential?
Well, so I published a paper in 2018 with a colleague from Denmark that said consequential modeling is always appropriate. So I'm going to stick with that.
So that's always harder. That's something that you don't finish, right?
Yes, it can be harder. And one of a colleague at the University of Arkansas whose critique of consequential modeling is, well, there's an infinity of things that could happen in the marketplace. Well, it's not true, right? We know, for example, that the marginal source of electricity in this country is always natural gas. We are not building new coal plants. We are not building new hydro plants. Anytime there's a change in demand for electricity, it's coming from natural gas. So the consequential modeling is simple in that case, right? If you're going to have electricity, it's natural gas. So an example, right, and where that matters is, let's say you want to build a new facility and you're trying to decide between Maine, Colorado, and Washington State. Maine and Washington have lots of hydropower. So if you're using an attributional model, you'd say, oh, we want to go to Maine or Washington State because we're going to get that low carbon footprint from hydroelectric power. Problem is, it's already all used all the time. And so you add more demand to the system, where does it come from? Natural gas. You go to Colorado, most of their sources are coal. Doesn't matter, we're not building another coal plant, right? It comes from natural gas. So in that case, right, the consequential paradigm doesn't help you make a decision, but it eases the pain of, there are other things then that you can consider in making that decision. Yeah.
For the consequential models, the things the demand is part of the model, but demand for future, how do you incorporate that? What's your plan for forecasting things?
Yeah, so that's a really good question. So LCA is limited to sort of small changes. You can't use LCA to say what would be the carbon footprint of the United States if we got rid of all of the animal production and we used cellular meat, right? LCA cannot answer that question because it's too large, too massive of a change in the entire economy would be necessary to get to that point. So you can ask, what if I make a small shift, right, towards a cell-based meat? What would be the consequences of that? And so you don't have to project, right, the whole system's demand. You're just going to ask what's directionality of this change rather than what will be the big change. I worked on a project with a colleague from UC Davis where the question was, what if ground beef demand drops by 15%? Well, that's too big of a change to answer by LCA, so we used a general equilibrium model, right, the GTAP model. We said, okay, what happens to the whole economy if you reduce beef burger consumption by 15%, right? There's all kinds of changes that happen. And then we said, okay, now let's do an LCA of the pre and the post, right? So you can do that, you can do things like that if you need bigger changes.
What kind of IAM do you find in integrated access model which use general?
What kind of IAM?
You said GTAP?
GTAP.
GTAP.
The General Trade Analysis Program. It's from Purdue. It's a model of the global economy.
Yeah, there are some other like GCAM, like I know some of them, but I don't know how can which one is better for just incorporating these kind of demands and using some part of the LCA integrated with them.
Yeah, I can't. I am not an expert in those equilibrium models. I know there are, in addition to the general equilibrium models, there are partial equilibrium models that, like IFPRI in Washington D.C. has a partial equilibrium model that's focused on ag sectors only. So that might be better for ag-related questions to do something that's a little bit more granular in the space. Sure.
In terms of management, you're talking about decisions that we make. But in sense of research, are we going to suggest things or will we just make everything clear? Because the part that is about weighting things is really something like about policy, about your insight. So the first question is that are we going to suggest something? The second part is that if we make everything clear, isn't it going to be everything going to be like a collapse in society because they know what's going on and policymakers are making decisions that everything is clear and so dark.
So, well, radical transparency is necessary, in my view. And fascinatingly, colleagues in industry that I work with have said the same thing, right? They haven't necessarily acted on it yet, but right, the principle of transparency I think is important. And I think the answer to the first part of your question is I am not the decision maker, right? I am the provider of information so that society can make an informed choice, right? So if I'm transparent and honest in my endeavors, right, and I say that this is, to the best of my or the LCA community's ability to say A is better or different than B, then society is going to make that decision, right? So as an example, where do we put our resources? Do we put our resources in water conservation or climate change prevention, right? Sometimes they're aligned and sometimes they're not, right? So that decision is not a decision that can likely be answered by the science we have today. So that's going to come down to a societal decision. Society will make a weight, right? By the choice of purchasing this thing or that thing. And then that'll transmit, through and decisions will be made to support what society wants to do, right? So, I mean, you can think about researching prostate or breast cancer, right? They're both important, but one of them gets a lot more money than the other. I'll let you guess which one. We're past time, so
Right on
thanks,
time.
guys.
Thank you so much again for the wonderful discussion.